Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Sean Welleck of the University of Washington and soon to be at Carnegie Mellon University, who will tell us about Llema, an open language model for mathematics. So as I always do, I offer to watch the chat. So you can ask questions during the talk. There'll be time for questions after the talk. But if you would like to get your question, looked at, perhaps a simple question answered, if you put it in the chat, I'll respond and ask it or give you a chance to ask it. So with that, Sean, please.
Okay, great, thanks. Yeah, so today I'm going to be talking about Llama, which is a new open language model for mathematics. And first, I just wanted to start off with mentioning that the projects that I'll talk about are part of a really amazing collaboration. So it's led by Jean-Guyer at Princeton, and it was with Eleuther AI, as well as people from many different academic labs. So a lot of people have become familiar with language models as a kind of platform for general purpose sequence-to-sequence generation. This might involve things like summarizing a document, generating code from a description, even having a conversation with a language model, etc. And something that would be really useful and interesting is if we could have this kind of general purpose sequence generation within a domain that we really care about. So for example, finance, medicine, or the one that I'll focus on today, which is mathematics. So there's been many different talks actually at this seminar about why this might be useful, ranging from helping to generate verified proofs. There was a talk about this actually just a few weeks ago, helping to solve different types of problems. Or there's a really nice talk coming up in December on having more open-ended interactions with a language generation system. So today I'm going to talk about a model that we trained called Llema. And just to give you a sense of some things that it can do, here's an example solution from Llema on a benchmark that is commonly used for benchmarking language models. So here, Llema hasn't been specifically trained for this benchmark. Instead, what we do is we prompt it with 4 different input-output examples. Then we give it this input problem and generate the solution with a standard inference algorithm. And so it ends up getting the answer to this one correct. And in fact, across the entire benchmark, it does fairly well. So just a year ago in October of 2022, there was a really nice talk again at this seminar on a model called Minerva. And so this was a really amazing paper from a team at Google, where they continued to train a kind of general purpose language model called PaLM on a fairly large data set of archived papers and math web pages. And as a result, the model's capabilities in math improved a lot. And so what we found here is that our model, Llema, kind of builds on this approach and is able to outperform Minerva on a per parameter basis. And then we also tried to go a bit beyond Minerva and support a wider distribution of tasks and data. So one of those in particular that we really want to have a special emphasis on is the area of formalized mathematics. So here, these are kind of specialized programming languages. You can think of them. Examples include Isabelle or Lean. And you can write math in the source code of the language. And then, for example, a proof can then be verified by the system. And there's kind of a lot of interesting work going on at the intersection of language generation models and formalized mathematics. So here's 2 example formal proofs that were generated by Llema. On the left is one in Isabel, and it generates this given human-written informal proof in LaTeX. And on the right is one in the Lean4 language. And in this case, the model is given the state, which is shown as a gray comment there. It generates a step, and then we get the next state from Lean and generate a proof in that way. And the really cool thing is, again, we didn't train the model specifically for this theorem proving task. Instead, we're again just providing it with a few input-output examples in its input context, and then it's able to some degree perform these tasks. If you stay around for the end of the talk and kind of don't fall asleep, or maybe you could wake up, I'll also show kind of a glimpse of where these types of models might be useful within a actual proof development. I'll talk about a tool called LLM Step, which gives you a way of hooking up a model like Llema and bringing it into the development environment so that you can get suggestions from it. Another big focus of this project is kind of not viewing it as an ending point, but rather as a platform for future work in this area. And so to that end, we try to make everything that we can openly available. In particular, the models, the data, and the code are all made publicly available. And so you can go to the GitHub page, and that'll point you to the various areas where these artifacts are. So it turns out that training a language model for math, I think, is also a really interesting machine learning problem. So I wanted to kind of motivate what we did a bit more precisely. So first, so that we're all on the same page, what is a language model? A language model gives us a probability distribution over sequences. So we can provide it with an input sequence, like a prompt. Then it gives us a distribution over outputs. And then the mapping between an input and this distribution over outputs is learned, and it's determined by parameters that are kind of organized into an architecture like a transformer. And then the really important thing about a language model is the data set on which it's trained, because that'll determine the parameters. So in particular, the way these are trained in the kind of standard case is we want the model to, we want to find parameters that make this data set highly likely under the model. And so there's various ways to interpret this or think about this. One is that we can view the sequences that we have in our training data set as being samples from some underlying true distribution over sequences. And then it turns out that this objective is equivalent to doing distribution matching in the sense that we're finding a model which minimizes the KL divergence between the model and this underlying target distribution. So then to actually use this for different tasks, like the ones I've been talking about, we use an inference algorithm. So for example, we present the model with an input prompt and then use something like temperature sampling to sample an output. And so with this kind of one page of notation in place, we can think a bit more precisely about how we might build a language model for math. And the first approach we could think about is just training a really good generalist model. And one property which makes this an interesting idea is that we have a really good way of making these language models better. In particular, increasing the amount of compute that we use at training time. By that, I mean training the model on more tokens and or increasing the number of parameters in the model, predictably will improve the language modeling performance. And again, This seminar seems to have a lot of great talks. There's a really nice talk on these so-called scaling laws that give you ways to make these predictions. So the natural idea is, why don't we just let our data set be as general as possible, and then be sure to include some math as a subset of that data, and then just increase compute as much as we can. So just train the model on more and more data, make it bigger and bigger, of course, up to our compute budget. Now, as you can imagine, this experiment starts to get expensive. So we can kind of look at experiments that are available to us. And one example is a model that was recently released by Meta called Llama 2. So the smallest version has 7 billion parameters, and it was trained on 2 trillion tokens of what you might think of as general domain data. So this includes web pages, GitHub, but also certainly does include some math, because there's certainly math on things like Wikipedia and archive. Now it turns out that this approach does work. The model will improve over time, but it might not be the most efficient way of getting a kind of specialist model for a domain like mathematics. So what this is showing here is, on the x-axis, the amount of compute that we use during training. And then on the y-axis is the accuracy that we get on the math benchmark that I mentioned. And so you can see the blue dot here, even with a 7 billion parameter model that's been trained on 2 trillion tokens, the performance is still fairly low on this benchmark. Then the purple line shows what happens if you keep training the model on another 500 billion tokens of code data. That's the Code Llama model. And you can increase the compute even more by just redoing the same thing with a larger model, a 34 billion parameter model. And that's the Code Llama 34B point right there. And so you can see, after expending all this compute, the model is actually worse than the 8 billion parameter Minerva model, and it's kind of far worse than the 62 billion parameter one. So we might need to think of a kind of new approach. So we can look at the scaling laws literature again, and it turns out that these models can still be very useful as a kind of starting point for becoming specialists on mathematical data. So this is a really cool plot from a paper in 2020 called Scaling Laws for Transfer. And what it's showing is that if you first start out by pre-training on text, that's shown in blue, and then your goal is to get good at modeling code data, then it's actually beneficial to start off by pre-training on text. And this reduces the amount of code data that you need to reach a given test loss. So for example, for most of the plot, the blue line requires much less Python data to achieve a certain test loss on Python. And so in other words, pre-training on a general domain distribution might actually make transferring to math more efficient. And so this kind of gives some motivation for the idea behind Llama, and it's the same idea that Minerva actually used. And it's collect as much high quality mathematics data as we can, and then start out at as good of a point as we can and transfer to this this distribution over mathematical data. And so concretely, the recipe that it turns into in practice is, we start out with the Code Llama model that I mentioned, and then we continue training the model on a new 55 billion token data set that we put together called Proof Pile 2. And so proof pile 2 consists of mathematical code, mathematical web data, as well as scientific papers from archive. And although 55 billion tokens is a lot, it's much smaller than the amount that these models are pre-trained on. And so we can see here that with a relatively small amount of additional compute for continued training, we could actually get a large jump in performance on mathematics. So so yeah, and then in particular, like the 7 billion parameter model starts to outperform Minerva at 8B, and then the 34 billion approaches the 62 billion parameter Minerva. So clearly here, the important thing, one important element of the recipe is the data. So let me go into some more details on the data set called proof pile 2. So the proof pile 2 has 3 different subsets. We collect about 11 billion tokens of code, 15 billion tokens of web data that is specifically relevant or related to mathematics. And then we have 29 billion tokens of papers. These we take from a pre-existing data set of archive papers. And some considerations that we had in mind while putting the data set together. One is that, again, we wanted to kind of build a specialized model, but one that's not too specialized. So we wanted to have broad coverage of kind of math relevant tokens. And in particular, we wanted to be sure to include formal mathematics data. We also specifically decided to not include any model generated data, except for some that might be in the data without us realizing it. So it's a kind of interesting question how good the model can get on just data that we collect from kind of non-synthetic sources. And it's certainly an interesting research direction to explore in the future, how much better the model could potentially get with synthetic data. And then, of course, we wanted to make the data openly available. And so we derive it from openly available sources. So here's a comparison with the Minerva dataset. And you can see that the key difference is the new code subset that we add in, which I'll talk about next. So the code subset, the kind of creative name, I think Jean-Pierre thought of it, is called the algebraic stack. And it has data from 17 different languages. And we filter it to be kind of relevant to mathematical code. And it comes from 3 different sources. So one is filtered code from the stack dataset, which is a large dataset developed for what was called the Big Code project for pre-training language models for code. We also gather additional data from public GitHub repositories through the API. And then we specifically add in some additional proof step data that I'll go into some more detail in a bit. Here's the kind of pipeline that we have. So we take GitHub and stack data, and then we have 3 different types of filters. The first is just general filters for quality. For example, we noticed that, especially with mathematical data, with mathematical code, sometimes you'll have kind of large printouts of arrays or things like that. Or in like Jupyter notebooks, for example, there'll be images encoded as base 64. So we add in some general filters for quality. Then we actually go through language by language and create specific filters for trying to ensure that the data, again, is high quality and somewhat relevant to mathematics. Here, these filters are mostly based on heuristics. And they're all available in our GitHub repo if you want to take a look at them, possibly propose better filtering methods in the future. It's all there for you to look at. And then the formal proof data, we do something separate with. I'll go into a bit more detail about that in a second. And we get our algebraic stack data set. So this I kind of already mentioned, but yeah, I don't want to underscore all the effort that went into kind of manual inspection of data and trying to ensure that it was high quality. So we developed some tools for looking through the data, kind of systematically going through it, language by language. And yeah, you do run into a lot of quality issues, and so having these filters are certainly important. So for formal math data, in total, we have about 1.5 billion tokens of formal math related data. And so some of these are, things from the stack from GitHub. But we also wanted to add in, at kind of pre-training time, additional goal states that are used in the proof assistant. So if you're not familiar with these, on the left here is some lean code that a user might write while they're trying to prove this example. And then on the right here is additional information that's given to the user that's kind of kept track of by lean. And so this is really valuable for humans while they're writing the proof, but also for machine learning systems that try to automate theorem proving in these systems. And as you can see, the goal state kind of isn't visible in the raw source code that you would find on GitHub. So we add in proof states that are extracted from the Mathlib project in Lean, as well as the Isabelle archive of formal proofs and the standard library. Now, the second part of the data set is web data. And so this was actually built as a separate, its own separate project. And so there's a really nice paper on arXiv now called Open Web Math by Kieran, Marco, Jean-Guy, and Jimmy Ba. And the Open Web Math data set collects about 15 billion tokens of web data that's been highly filtered for mathematics. So here's a kind of overview of their pipeline. The overall idea is to start off with the Common Crawl data set. This includes a massive number of web pages, over 200 billion, and then have a series of filters and math-specific text extraction mechanisms to ultimately get at a filtered data set of about 6 million documents and 15 billion tokens. So again, kind of going into the details of this data set would require its own talk, and the Open Web Math paper is a really great read. Let me just highlight two really cool things from their data set. The first is that getting LaTeX from these Common Crawl pages is actually very non-trivial. So the largest source of LaTeX, they said, turns out to be MathJax. And in Common Crawl, the JavaScript required to kind of render the MathJax a lot of the times hasn't been executed yet. So they put a lot of work into actually getting the LaTeX from that source, and then identified 6 other sources where you could find LaTeX in these pages. And so a big part of ensuring the quality was actually building this kind of custom extraction. And then one of the filtering mechanisms that they propose is to use a model-based filter. So here they have a math score classifier that predicts whether a document is likely to contain LaTeX. So for example, with a document that does contain LaTeX, you can kind of remove it, and then based on the surrounding context, you want to predict whether this is likely to, have some math in it. You could also run the classifier on documents that are kind of related to math, but might not actually include LaTeX. And the classifier could kind of pick up on those as good documents to keep around. And then for the final portion of the data set, we use archive papers, and we source them from an open source replication of the Llama training data from the team called Red Pajama. So then to train the model, we have two different settings. So again, we initialize the model from Code Llama. Then we train the 7 billion parameter model for 200 billion tokens, and the 34 billion parameter model for 50 billion tokens. The code available to do this is online. We use GPT-NeoX, and it was across 256 40 gigabyte A100s. And yeah, part of the project involved adding in flash attention 2 to NeoX. And then we use a mixture of parallelism strategies. An interesting question is, whether we can get better performance by weighting the different parts of the data set in different ways. So what we did is to try out different weights for the different parts of proof pile. So the code, the web, and the paper subsets. So we ran some experiments, and they're in the paper, looking at the perplexity on a set of mathematical text with different handpicked weights. And ultimately we chose to choose the weight shown on the right. So as we kind of sample sequences for the model to train on, the web sequences will be upweighted relative to code, for example. Then we also mix in some just general code and language data. This builds on techniques that were also used in the Minerva paper, as well as other. I think the Code Llama paper does this as well. Yeah, so here's a picture of the validation loss. You can see the 7 billion parameter model is trained for more steps than the 35 billion, and it just gives you some sense of the training trajectory. So then to evaluate the model, we kind of split the evaluation into 3 different parts. So the first is kind of common benchmarks that are focused on chain of thought problem solving. So here we have a model generate a chain of thought or a kind of rationale followed by a solution. And then it has to solve a problem without using any external tools, like for instance, a Python interpreter or a calculator. Then the next 2 involve using computational tools. So either doing similar problem solving, but now with access to a Python interpreter, or doing formal theorem proving. And our goal was to kind of evaluate Llema as a base language model, not one that's been fine-tuned for any particular task. So in all these evaluations, we evaluate the model by providing it with between 3 to 10 task examples in its input prompt. And yeah, I should also say that especially for this first part, part of the goal was to reproduce a very similar evaluation setting to what they had in Minerva. So we also do things like implement the answer checking based on Minerva, use their prompt to try to get a very fair comparison. So you can see here that Llema improves over the base model that we started with, Code Llama. And this is showing the 7 billion parameter model. And you can see across all 4 of these problem-solving data sets, it performs fairly well. Then if you go to the larger model, the 34 billion parameter one, and also use a different inference algorithm, this one is called majority voting, then in absolute terms, the performance improves a lot. And the model is actually performing pretty non-trivially on this math data set, getting above 40% performance. And you can see that the 34 billion parameter lemma is kind of approaching the performance of 62 billion parameter Minerva. So as I mentioned, we focused on the kind of few-shot evaluation setting. But another way in which these base language models can be useful is if we do actually have data for a task that we care about, and we want to fine-tune the model further. So we did some preliminary experiments in this direction. Here, this is showing what happens if we fine-tune the Llama model on this data set called MetaMath QA, which targets performance on the math benchmark and GSM 8K, versus if we start with Llama and then fine-tune it on the same data set. And you can see here that Llama actually served as a better initialization for further fine-tuning. And also the performance of Llama improved further after fine-tuning on this MetaMath data set. But yeah, I think this is a really exciting thing to explore further, and there's certainly a lot more to do with fine-tuning. Another really cool thing is that by having all the data available and making it available, we can do more careful analysis and have others study this further on the overlap between the proof pile 2 and test examples. So we did some of this analysis. We did some analysis in the paper. What we did here is to look at for either math problems or solutions, whether there was a 30-gram overlap between the problem or the solution and a document in the proof pile 2. We also tried this with 20 grams and found more false positives. We have some examples in the paper. But we do find that in some cases, problems from the math test set in particular, these come from high school level mathematical competition problems. And so they do appear on some of these math web pages. We did a small study where we looked at 100 of them. Sometimes there's no solution, or there is a solution kind of discussed in a forum post or an alternative solution to the one that's in the evaluation set. And you can see the numbers here. So out of 5,000 problems, we found some hit or some overlap between problem statements, between 348 problem statements and then 34 different solutions. Then we could see kind of how this overlap actually impacts performance. And what we did is evaluate Llema on problems that had a hit, so problems that had a 30-gram overlap, and then problems that did not have a 30-gram overlap. And interestingly, we didn't see any consistent difference in performance. So in particular, on the right, this is showing by the difficulty level. On the right is the most difficult set of problems, level 5. And the model still finds these very challenging in both cases. And then for the other levels, it's a kind of toss-up. Sometimes one is better than the other. So again, we made the tool for doing this analysis available as well. And I think this is a really exciting direction to kind of better understand the relationship between the data that the model was trained on, and then the ultimate generations that we get at evaluation time. Then as I mentioned, another focus was formal theorem proving. So here's kind of a lot of text, but let me walk through it a bit. We evaluated the model on 2 different formal theorem proving tasks. So in the first task, the model is given a kind of natural language or LaTeX problem statement, as well as a LaTeX informal proof, which is shown at the top. And then on the left, the model has to generate a proof in Isabelle, and then it's checked by it's checked by Isabelle. And then on the right, this is just a purely formal setting where we don't use the informal proof at all. And the model is given this proof state, which is shown in gray. Then it has to generate the next step of the proof, and then you continue until either you fail or you reach a correct proof. So let me just talk, in this talk, let me focus on the formal to formal task. So traditionally, this is done, well, I say traditionally with language models. It's traditionally done by having the model predict a next tactic, which you can think of as the next step, given a proof state, and then to use it within a best first search algorithm. So we essentially query the model for multiple possible next step candidates. We score them and then perform the search until it either times out or we reach a correct proof. So what we did is to kind of simulate this approach, but to do it few shot. So in particular, we provide Llema with 3 different examples of states and next tactics in its prompt. And then we kind of run the standard best first search algorithm using this few shot version of Llema. Here's showing some results on a benchmark called Mini F2F. So Mini F2F has 244 test examples that come from different mathematical competition problems. There's some also from undergraduate coursework. And this is showing a range of methods. Let me step through some of them. So in kind of orange and yellow here is the Code Llama model, which is again prompted few shot. And then all the way on the right is the Llema model. And this is showing the total number of theorems that were proven out of the 244 theorems. So one cool thing is that we actually approached the performance of a model that was fine-tuned for tactic prediction and additionally uses retrieval called reprover. And then we also include, I also include in this bar plot some numbers from other work. It's from a paper called Copra. That's shown in purple, gray, and blue. So those bars use a slightly different search procedure, but it does give you some sense that the performance that we get with Llema is, fairly non-trivial and pretty interesting, considering we're doing it in this few shot setting. So next, I wanted to, kind of give some glimpse of where a model like Llema might actually be useful, how it might actually be used in lean proof development. And so for that, I wanted to talk about a tool called LLM Step. And kind of at a high level, LLM Step gives you some way of integrating a language model into Lean. And what we can do is we could send a proof state while we're writing a proof, and also send the entire document context, and then just come up with different prompts for Llema, and then have it send back suggestions for what to do in the proof. So it's always risky giving a live demo. Hopefully it still works. But let me just see if it works first. Okay, yeah, so here it is. So here is looking at VS Code. And this is just a really simple proof here. What we're proving is that essentially transitivity, that if R is a subset of S and S is a subset of T, then R is a subset of T. And so what we do is we actually have a tactic called LLM Step. And what this does is it sends a request to a server that's running an instance of Llema. And Llema gets this proof state, and we also send it the document, the code that's in the document that you're working on. Then Llema generates some suggestions, and then we can check them in Lean. And so you can see here the ones in green actually complete this proof. If you're not familiar with Lean, this no goals means that the proof is complete. And we kind of got this proof from Llema. Now, a really cool thing is that, again, since we're in this prompting setup, we don't have to just give the model proof states. We can also just try giving it all of the code that's in the document. So here's a maybe less trivial example. Maybe I'm embarrassing myself because this is from a kind of personal project. I was formalizing some probability. And for whatever reason, I wanted to define my own probability mass function. And so this actually differs from anything that is in the MathLib training set that these language models will be trained on. And here's an example that I put in this file where we have kind of one more step in this proof, and we can ask Llema for a suggestion. And in this case, it actually gives us a suggestion that uses this definition that I created up here in the file. So again, this only appears in my personal project, and we basically sent the context of the file that I'm working on to Llema, and it came back with a suggestion. So yeah, that's a little, let's see. Let me go back to presentation mode. So yeah, so this tool LLM Step is available on GitHub. And in general, you can, I don't know what's happening here. Sorry. Yeah, so in general, you can run one of these servers on CPU, GPU, or a Colab notebook. I should say that the version on GitHub that's more stable actually uses smaller models that have been fine-tuned. And so currently, Llema, I'm making the code available, but it's very much experimental. It requires some engineering to some engineering fixes. But yeah, you can check this out if you're interested. So in conclusion, I talked about a kind of recipe for specializing a language model to mathematical data and tasks. And in particular, talked about a model called Llema, which involved further training Code Llama on a new data set called ProofPile2. And Llema kind of has good performance on mathematics. And I think really moving forward, the exciting thing is that this could be a platform for further research in this area, since all of the code, the models, and the data are made openly available. And then, of course, as I mentioned at the start, this was part of a really amazing collaboration with an amazing team. And so, yeah, reach out to any of the authors here, and I'm happy to take questions now.
Oh, great. Thanks, Sean. That's really interesting. Are there questions from the audience?
So I have a couple of minor questions, if that's okay.
Mm-hmm.
So one is that, so you mentioned that one of the models used a closed source archive, and the advantage of your model is that it uses open source archive. And you mentioned this repository, Red Pajama, that has this open source replication. That's mysterious to me, so I'm curious how that works, how you take something that's closed source and putting it somewhere else somehow makes it open source.
Oh, yeah, that's a good question. So, so I guess in the table I had where I had the X, I just meant that like the specific instance of archive that was used in the training of Minerva, we don't have access to. So it was more saying that like if someone wanted to look at exactly what we used to train Llema, then now like the instance of archive that we used is
I see.
openly available.
Okay. So archive is generally generally it is open source. I see. So you can it's just you just have a snapshot of what you actually used.
Mm-hmm.
And then the other small question is, at some point you mentioned this measure of perplexity, which is a word. I like that phrase, but can you say something about what perplexity is?
Oh yeah, so I guess at the starting I talked about how you train the model, which is to essentially increase the probability of a sequence in the corpus. And then this turns into, at each step of the sequence, increasing the probability of the next token. And that's actually the loss function. So what perplexity is it's proportional to this loss function. So it's going to be proportional to the probability that your model is assigning to the next token in some corpus that you have. So you can take a held out test corpus and then take your model and then measure its probability on kind of each next token. And then perplexity will be proportional to that.
Thank you.
If I can add, it goes back to Shannon. I think it is exponential of the average entropy. So in some sense, it's the average number of equally likely words for a prediction. So lower is better.
Mm-hmm.
More questions?
Question. So I didn't understand when you said you gave links to GitHub, but so we could go and have a look at your repository. But do we need to register for anything, or is it really anyone can play with your tactic proposing next steps?
Oh, for the the LLM stuff?
Yeah, LLM step.
Yeah, so that one can be it can be used by anyone, and there's a few different settings. So the one that's in GitHub right now, which is kind of the main version, will download a model that's been fine-tuned for tactic prediction. And then, yeah, assuming the setup instructions are okay, and let me know if they're not, then you should be able to import LLM step into your own project. And then the one thing you have to do is start a server that is running the language model. And so again, there's different options. So you could run a smaller model on CPU, or if you do have access to a GPU, run one of the larger models. And hopefully over time, yeah, we'll have ways of running the larger models on CPU, but that's kind of where it's at right now.
Okay, thanks.
I have a question about, you mentioned formal to formal, and I was wondering if you see this technology as a way of translating from one formal setup like Isabel to lean and back, or if it's how successful could it be in this setting if we wanted to not necessarily have to build math libraries for each system or try to connect them? Is this something that you see as realistic?
Yeah, I think that's really interesting. So a lot of the times we might have, a useful library in formal system A, and we kind of want it in formal system B. So yeah, I would say like as of now, this is kind of there's a lot of potential here, and especially now that we have a model that has kind of done some amount of large scale pre-training on multiple languages. Yeah, I think it's a promising thing, but it certainly requires there's different levels of difficulty, right? Like translating an entire project into another language could be quite challenging, I think.
Thanks. Yeah.
I have a question about the example you showed on LLM step. You were able to use the new definition that you put in there. So you just put the whole file into the context of the language model? Is that how that works?
Yeah, so what it's doing under the covers is it's sending the state and the file up to the given point. And then it's running Llama twice. So it's running it once given the state and then once given the file context. And then we just send all the suggestions over.
Does that typically fit in the context size that you have for your models?
That's one of the that's why it's experimental right now. So if you use it on larger files, it could exceed the context. And so we need to figure out like what is the best pattern for doing that, because it could still be useful on shorter files.
John, could you say, just for those who haven't really tried to run Llama, and I assume this is the same resource requirement. Suppose you do have like 1A100 and you want to do a query, an inference. How much time does it take?
So that's a good question. So there's a really cool library called VLLM, and it runs on, if you have a supported NVIDIA GPU that can use VLLM, then the inference can be quite fast. So we ran some benchmarks, and the queries were around 1 second or less if you're running on a suitable GPU.
Okay, great. And that's with like a 2,000 or a 4,000 token window, something like that, or?
We haven't. I don't have exact numbers for as the context length grows, but maybe that it gives you some sense. If you run it on without VLLM, it'll be much slower. But
so VLLM.
The examples I was giving are just running on one GPU, and those were coming back. You saw like relatively quickly.
Yeah. More questions?
Hi, Sean. I'm not sure if this question has been asked already. I'm wondering, how does this different from, say, a few recent large language models on mathematics, like wizard math or Mammoth or MetaMath?
That's a good question. So Llama is, you could think of it as a base model, so more similar to Code Llama, in the sense that you can still prompt the model for a variety of tasks given just input-output pairs. And then you could additionally fine-tune it more with something like instruction tuning. So the models like Wizard Math or MetaMath, those have already been fine-tuned on a kind of data set that's specialized for particular benchmarks. And the one experiment we have is to actually take Llema and fine tune it on, I think it was I'm already forgetting the MetaMath dataset. And it serves as a kind of better initialization than Llema. Than Llema.
Thank you.
Questions?
I have another one. So for the formal to formal task, you emphasize the prompting approach, but you do have some data specifically for this task that you put in there, right? Like, I guess I'm wondering, how is that data different from like your few shot examples that you were giving?
Yeah. So the data that involves the states is from MATLAB. So yeah, for instance, like unfortunately, we didn't want to evaluate on MATLAB until some more theorems come out, but we evaluate on Mini F2F. And then the particular format is a bit different. So the pre-training data has more metadata in it, if you take a look at it. So yeah, the model is still kind of adapting to a new input-output example task in that sense.
Do you think it would do a lot worse with, I guess, I mean, you also said Isabelle data, so I guess it would probably do well in Isabelle too, but like Talk or Agda or something like that?
Yeah, that's a good
like,
question. We haven't tried it out yet.
More questions? Okay, if not, well, let's thank Sean for very impressive and I think very useful work that will stimulate a lot of further research. So thanks everybody. We will not have a talk next week, and then the week following, November 8th, we will have Gabriel Poesia from Stanford, who will talk about his system piano. So I look forward to seeing you all there. Thanks.
Okay, thanks.
That's great. Let me kill the recording here.